to Professor Gerd Ascheid. He's our keynote speaker for today, and he has a very good record and expertise. He has earlier co-founded a startup which successfully brought a system simulation tool to the market, and this was later taken over by Synopsys. And he had spent some time working in the Silicon Valley-based EDA market, where he was a leader for 9 years, and he acted as a director. At that time he was responsible for ASIC design projects for advanced wireless communication systems, including DVB, 3G, and microwave radios. And since 2003, Professor Ascheid is a full professor at the Institute of Communication Technologies and Embedded Systems at Aachen University at the Wireless Center, RWTH. And he has co-authored 3 books, published numerous publications, more than 250, and journal papers and international peer-reviewed conferences. And the area of his expertise is digital communication algorithms, signal processing, and ASIC implementation. He's also co-founder of more startups than the one I mentioned, and the most recent is still active in the domain of smart cities. So I think that we are going to have a very interesting talk. And please, you have 1 hour for your keynotes.
Thank you. So I think everyone can read the title, hopefully. And I probably not try to stick too much to the microphone because that makes you somewhat too static. And I guess I can talk loud enough from the experience with lectures in Germany. As I just mentioned, Aachen University is quite a big university, so we have something like 43,000 students currently, and in electrical engineering there are about 750 to 800 students starting each year. So the lectures typically have a larger audience, so you have to talk loud anyway. Okay, so to come to the topic of my keynote speech. Cost of information, how many bits per processing energy. This actually is a bit based on my background. As you have heard, I was with the company Synopsys, and I was in ASIC design and wireless communication. And actually, I would like to take you onto the bridge between ASIC implementation on one side and wireless communication on the other side. Because this bridge is not new, this bridge has been there for a long time, but it's often ignored its existence. So, I guess, no, okay. Okay, so as I mentioned, CMOS, which is the leading digital technology, and wireless are not independent. It's a joint success story that we had in the past. Okay, I have to do it like this. So this is a not very new figure. You see it ends in 2010. We will look into the future during the time of this talk anyway. And this just shows that the number of transistors that we can put onto a silicon die shows this kind of linear increase, but the left axis is a logarithmic axis. So it's a linear curve on a logarithmic axis, so it's an exponential growth that we have. And it's really amazing and impressive. This exponential growth has existed for almost 4 decades, and I don't know any other technology which was able to support an exponential growth over such a long time period. I don't want to go into the details, it's just this growth of what we can do with time. And a well-known colleague from Germany, Gerd, also put this nice figure together, which shows how the data rates for different wireless technologies, whether it's short range, or Wi-Fi, or cellular, has also grown exponentially over the years. And this is not independent, because this was enabled by the improvements in CMOS technology. Now, you notice that this is predicting until 2020, which is not too far from now. And also this paper was from 2011, so 5 years ago. So it's since then some things have happened, and also the forecast has been extended. So the scaling is not just supposed to end in 2020. Actually, I think what you can say today, most people agree that it's going more like to 2025. And it's going down to something like 5 nanometers around that scale, which is, as we will see later, a very small distance. So I just would like to stop this at this point here and come back to this later. Because as we see, there is a scaling until 2025, so we could expect everything is going on as it did in the past. No need to worry about implementation. Clever ASIC designers will be able to solve all our problems. That's not the case today anymore, and I would like to show this a little bit with an example that we have done in the last years, and where we have tried to really see what happens if we do the best and the top processing that's possible. What does it mean for technology? And the challenge that we have selected, this is now coming to wireless communication, was MIMO detection. So we have multiple antenna systems, well-known technology, and we also know when the transmitter knows about the channel, we can use singular value decomposition and so on. But if that's not the case, we have a slight problem in the receiver. So we have a data stream X, we transmit it over NS antennas. On the channel, the signals will mix. And in the receiver, we have NR antennas, and each of these antennas receives a bit of this mix. Because usually it's based on OFDM, it's narrowband per subcarrier, so we can assume a flat phasing channel. We can assume that it's just a complex multiplication that happens in the channel. And so we have the well-known model which describes the received signal as a vector, one component for each antenna, and the channel is a matrix, the transmit signal is a vector, and the noise vector. Now the problem, the well-known problem is, as it's visible here, the signals are mixed, and how can we separate them again? So nothing new. That's why I think I don't need to go too much into the different technologies. I will discuss some options later to see the complexity that we have. Well, first thing is then we take these streams, we try to separate them, we get the symbols back, and from the symbols we get the bits, the coded bits, CN. They are fed to a decoder because any reasonable wireless communication system needs error protection, so we have a decoder. How can we do this? Well, simplest thing would be zero forcing, which means we just take the receive vector and multiply them with a Penrose inverse or pseudo inverse matrix here. Or if you want to do it a bit better, if you want to take the noise in addition into account, you have the MMSE, so it's looking very similar. You just, in addition, take the signal to noise ratio in there, but that's not it. So what does it mean? What are we doing here? What's the complexity? Well, as you see, there is this to the power of -1 of a matrix, so it's a matrix inversion that requires some extensive processing, a little bit challenging, but fortunately, we only have to do it when the channel changes, so it's something that's not required as frequent. What's more frequent is, of course, that every receive vector that we get, we have to multiply, so this matrix vector multiplication. These are the two operations. This is something that can be implemented very effectively. Actually, any graphic processor is built to do that, or you can build hardware to do this. That's fine. If you want to do the optimum, it's getting a bit more complicated. In this case, we would have to do maximum likelihood demapping, and you see already there is no longer an explicit equation. That's more an implicit equation. So find the minimum, or find the x which minimizes the Euclidean distance, y minus hx. So you have to try all x, and this can be a lot. If you assume 64 QAM, you have 64 to the power of 4 different versions, so it's quite a lot of computation that you would have to do. Fortunately, people found some clever solution which makes life easier, which is a so-called sphere decoding. You do some modification, the so-called dual decomposition of the matrix, which is at the lower left. And the result is a matrix R, which is upper triangular. Because it's upper triangular, you can simplify this search. You don't have to search all alternatives. And it's okay, make it possible. I don't want to talk too much about this decoding. It's something that's well known, not you. It's just to give an idea of the complexity that we face here. And what is the complexity? Well, the complexity is that we have to go through a tree of possible solutions, that we have so many solutions, and we have to organize this tree search in an efficient way. So it's a lot of control and stuff like this. And therefore, people were looking for some optimizations besides the sphere decoding. So you can do some suboptimal stuff like only following some best options, and that reduces the effort. But this is suboptimal. So if we want to go for the optimum, we have to do this full tree search, and that makes the system much more complex than this previously shown matrix vector multiplication. Now, so far, we have assumed our idea is to get the coded bits back. But actually, that's not the best we can do, because most of the decoders that we use today actually benefit when we give them not just the bits, but when we give them reliability information. So instead of passing the code bits, we pass reliability information for the code bits to the decoder, and that is the next improvement. If we do this modification, life gets even tougher, because what we would have to do is something like this. Again, don't worry about the details of this equation here, it's just to demonstrate how complex this actually would be. You see a sum over exponentials and so on. So if you would have to do this in real time for 1 gigabit per second, you can imagine that you need a big set of computers to be able to do that. So nothing that you can carry around. Fortunately, again, the algorithmic guys found some clever solution, and this is also the well-known max-log approximation, where you actually approximate this upper function by each of these sum over exponentials by the Euclidean distance, or by the solution which gives the Euclidean distance. What we note here is that now we are back to maximum likelihood, because there the equation was also find the x which minimizes something here. So when we want soft information, we cannot get around this implicit minimization, so which does not tell me y or x equals, which means try all x. So whenever we want to use soft information, we are somewhat stuck with this more complex operations that we need. Okay, but it's possible to do it. There were proofs, there were implementations that showed it. But it's not yet the end of the road. We could actually do better, because when I briefly go back to maximum likelihood is only optimum if every x is equally likely. But we are using a code, so there are code words, and there are bit combinations which can exist, and there are bit combinations which cannot exist. So actually we should restrict ourselves to the possible combinations. But this is completely unfeasible. However, there is some approximation which is often used in such situations. We go for iterative processing. So what we do is we do a regular mapping, provide the soft information, do the decoding, and then the decoder tells us, okay, from what I see here, these are more likely code words and these are less likely code words, so the probabilities of the bits, we have more information about it. And now we could go back and say, oh, okay, now we have some knowledge about the probability of the different bits in our and we could use them for better demapping. With this better demapping, we do another decoding round, and after some time, after some rounds, it will converge, and we finally get the decoded bits. Just as a side note, when we do this, we have an iteration, and this concept is not new because a lot of the codes today use already iteration. So whenever you do turbo decoding or LDPC decoding, they also use iteration for the same reason. So it's conceptually it's more or less the same, just extended one step. What is the penalty? Well, we have to consider this additional information that we get from the decoder in the demapping. So our demapping gets an additional term. It looks a bit challenging because we have natural logarithm of probability. Fortunately, the probability is exponential, so the whole equation is not as complicated as it looks like. So that's good news. But the bad news is we still have to do this minimization, and the organization of the minimization, for reasons I don't discuss here, are more complicated now. Without this additional information, you can organize it quite well and very effective, but with this additional information, the organization becomes a bit more complex. So these are the prices that we would have to pay for it. And we have the price that we do iterations, that we do demapping and decoding several times. So that increases, of course, the complexity. If I only do it once, I have basic complexity. If I do one iteration, I have to do it twice, so it doubles my complexity. 3 iterations, triples, and so on. So the complexity here is, again, this research and the calculations that we have to do. Now you could say, how about this MMSE? Could I, because that was simpler from the starting point, could I use this? Could this make my life easier? Unfortunately, for instance, colleagues from Lausanne, they have analyzed this, and it's about the same complexity, so you don't save a lot, because considering the feedback in MMSE makes this also more complex, and then you end up with something similar as if you used it here. So it's from that point of view not a especially complex solution, it's just what you have to do when you want to become iterative. So the first question now is, when we make life more complicated, does it give us any advantage? And I don't want to analyze this in full detail, because then I would have another half-hour presentation on bit error rates and so on. So I just want to do it in an indicative way. You see here some curves, and the red ones are showing this MMSE concept, and the blue ones are showing the sphere decoding that we have implemented. And what you can see is the straight lines on the right-hand side. This is if you just do one forward pass, so when you do it the standard way. If you do iterations, the bit error rate curves move, or the frame error rate curves, sorry, move to the left. So you see that you gain significantly. It's in the order of 1 dB to 2 dBs that you gain by this iteration. So it's not like using iterative receiver doesn't pay off from the performance point of view. So definitely the answer is yes. Using this more complex iterative processing improves performance. However, the question is it really worth this effort? From a performance perspective, yes, but how about this implementation cost that's around it? So the best way to find it out is to try it and see what happens. So what we have done is we have implemented a decoder like this that's doing this iterative demapping. And fortunately, we didn't have to start from scratch totally, because in an earlier project, we already had looked at a detector manual demapper, which was able to take soft input from the decoder and provide soft output to the decoder. So it was the basic building blocks for the demapping, for an iterative demapping. We have studied this separately, but of course the interesting approach was how can we combine this into one with the decoder. Now it would have meant to build a decoder, but fortunately we had a good relationship with the guys in Lausanne, EPFL Lausanne, They already had implemented a suitable decoder, and they were interested in the collaboration, so we jointly did this and used the two designs for a final iterative decoder. Now, using the two designs does not just mean take them, stick them together, and you're done. Actually, it's a bit more complicated because now you have iterations. So the mapper provides information for the decoder provides new information for the demapper. So they have to talk to each other. Well, this sounds like it's split into two. You have the decoder, you have the detector, and you have two memories. One for the detector and one for the decoder. But what the detector produces as output is input to the decoder and vice versa. So the not too very far away idea is we have both options for the memory connection. So there can be a straight connection. That means the detector writes into the upper memory and the decoder reads from the lower and writes into the lower. And then at some point in time we swap. And the detector then takes the output of the decoder, which is down here, and reads from here, and in parallel the decoder can take the output from the detector. So with this simple organization, we can just handle the two memories that are just swapped in their relationship. This sounds very simple, but unfortunately code has other frame lengths and other organization than a detector. The bits are not in the same position to the symbols and so on. So it requires a bit more work, but again, this would be a very long presentation to talk about the details and what's published in such things. That's one thing. The other thing is the decoder, LDPC decoders typically, it's known up to 10 iterations that that's it. Unfortunately, the MIMO detector, because it does a tree search, you never know how much you can prune in this tree search. If you have a good condition channel, you are finished very fast. If you have a bad condition channel, you may have to go through all parts of the tree and will not be able to prune a lot. So it can take much longer. And in general, the demapping anyway takes longer because one demapping process is one symbol, is a few bits. And PC decoders typically work on several hundreds or thousands of bits. So the lengths are different. How can we solve this? Well, the easiest thing that you do in this case is you just have multiple instances. So we found out that if you use 5 cores for the demapping, then there is quite some balance in the speed between the two, and it works. Okay, and this thing was designed with all details and manufactured, and then we actually did measurements, real measurements of the performance and also of the power consumption to get an idea of what happens. As it is built, it supports up to 4x4 MIMO systems, up to 64 QAM modulation. It was about 1.5 million gate equivalents from the size. And as you can see, the detector and the decoder are 2 to 1 roughly. So the detector takes roughly twice the number of gates as the decoder. And there is, of course, the memory in the middle. Frequencies that we had to use was quite reasonable, and actually the maximum information throughput was more than 1 gigabits per second. So you can really do iterative demapping with 1 gigabit per second. It's possible. Okay, so that's good. But still the question is, does it really make sense? Because there is a penalty behind it that I didn't talk about so far. If the CMOS device switches, it consumes power or energy. I should say for one switching, it's energy. So what happens when we measure the energy that is required per bit to decode 1 bit? Of course, it's an average number. And these are the curves that you get, and they are somewhat interesting to look at, because when you look at the decoder, this is the dashed line at the bottom, the lowest one. The detector is the dotted line, and the total system is the solid line. On the left-hand side, we have the picojoules that we need per bit, and at the bottom, we have the signal-to-noise ratio. Now we can imagine when the signal-to-noise ratio is good, you don't need iterations. You can prune a lot. Your STI decoder is very efficient. The LDPC decoder doesn't need iterations. It just gives the right bits in the first round. So energy per bit is very low. But then when you reduce the signal-to-noise ratio, the decoder has to do more iterations, which means that for every iteration, the power increases, the power consumption increases, because more iterations means more calculation. And the detector also has to do, can do less pruning, so this requires more work, so its power consumption also increases per bit decoding, and it goes up. The relationship by itself is somewhat reasonable, because the ratio in the range up above 22 dB is roughly 2. So the detector needs just twice as much as the decoder. I think that's acceptable. That makes sense. But if we come to the lower signal-to-noise ratios, then it starts to increase. So the mapper has to do more work. It's tougher for the detector, and it's going up to a factor of 6. And you see overall, the energy that is required to decode one bit goes up, and this is a logarithmic scale. It's not a linear scale, so it's a significant increase. So the penalty for this processing in terms of power is pretty high. So the conclusion from this is to get the best performance is most expensive for low signal-to-noise ratios. For high signal-to-noise ratios, it's easy, but for low signal-to-noise ratio, it's expensive. So now we actually have two possible optimization goals. We could say, don't worry about the power consumption for whatever reason, it's not relevant, just optimize the communication performance. But there may be other situations. I mean, every one of you knows when you have been around and you use GPS and thinks your battery is starting to get empty, and then you might prefer that your system works with optimized processing energy efficiency and less, maybe less speed should be okay then. So that could be the other optimization goal. And we have looked at the results in this way. The first thing is, how do you compare? You could compare the bit error rate that you achieve, but that doesn't tell you anything. You have to code decoding in the way. You could look at the throughput, but then you forget about the bit error rate. So the best thing is just look at how much information did I really get. So how much correct information did I get? And this is the good put. So it's the symbol rate, it's the bits that we have per symbol, it's the code rate, the number of antennas, because it transmit antennas, because that tells us how many data streams we have in parallel. And then we have a loss. These are the erroneous bits, so 1 minus the block error rate. That's the other factor, and these are the bits that are received correct. Okay, this is the good put. So for a wireless communication engineer, lots of interest is the spectral efficiency, meaning how many of these good bits do we get per second per hertz bandwidth. So we divide this by the bandwidth, and that gives us a spectral efficiency. But now we have the implementation. So there is an additional measure, and that is the energy efficiency. That is, how many bits do we get per power? So, or bits per second per power, and bits per second per power is the same as bit per energy. Because the second then goes into the watt seconds, which is joule. So it's the bits per nanojoule. If we now use this design to do an optimization, what you see here is the spectral efficiency in terms of bits per second per hertz that we get over the signal-to-noise ratio. And you see the solid line. This is when we go up to 6 iterations. This is the real best we can do. After that, typically it's converged, and when you continue to iterate, you don't get any improvement. So you can say it's close to the ideal curve. You see that it's an increasing curve, and you see also indicated the points where we switch from 4 because when the SNR gets higher, then of course we can use higher modulation scheme here. So that would be the view of the communication engineer. And then we look at the energy efficiency, so the bits per nanojoule. And what we notice is that, again, when you look at the curves here, it's low in the beginning. So for low signal to noise ratios, we get only very few bits per nanojoule. So it's the energy efficiency is low. We need a lot of energy to do it. Then towards 10 dB, we see that it's increasing, and then all of a sudden the energy efficiency drops. Why does it drop? Because at this point, from a communication perspective, to get maximum spectral efficiency, it's advisable to switch to 16 QAM. But at 10 dB, 16 QAM requires quite some processing to get low error rate. So we have a low spectral efficiency. And then at around 20 dB, it gets better again, but then comes the point where we switch to 64 QAM, and again our efficiency drops. So what we said before, low SNR always means low energy efficiency. And it depends, of course, on the SNR and the modulation scheme that we use there. So we have done two different curves here now. The red one is the one that we just discussed. So in the upper figure you see the spectral efficiency and the lower the energy efficiency. Now you could say, well, I would like to minimize my processing or maximize my energy efficiency. That would give the blue curve. So what would happen? Actually, at 10 dB, we would not switch to 16 QAM. We would actually stay with 4 QAM because then the energy efficiency continues to increase. And only around somewhere there at 9 to 20 dB, we would actually switch to 16 QAM. And also the switch to 64 QAM would occur later. So you have the choice what you want to do. Energy efficiency or spectral wireless efficiency. And that gives you completely different rules how to switch between modulation schemes. You could ask why the blue curve here in this range is above the red curve where we are at 4 QAM. This is because we switch to different codes in different points. Because implicitly we also have assumed that the code rate changes from here to here. Here we have a lower code rate than here. So that's what makes this an additional point. And the comparison is interesting because for a spectral efficiency gain of 2, so just to double the throughput, you have an energy efficiency penalty of 10. So it's 5 times more expensive, you could say, from an energy perspective. And actually, the PhD student who did this measurements, he also put a nice figure together, which looks like this. So he said, okay, now with these numbers, I say I'm willing to sacrifice my battery lifetime by 10%, so that it's shortened by 10%. That's okay. That tells me how much additional energy is available. And now from the battery side, I can say, okay, if I have a smartphone with a smaller battery, then this is the range where I would use which kind of MIMO stream here. If I would go for higher symbol rates, I should not, or let's say if I want a higher symbol rate, I should actually not use 4x4 MIMO. From a communication perspective, you would go to 4x4 MIMO because you have 4 data streams, so you have a higher rate. But from a processing energy point of view, this is disastrous because it requires a lot of power. It drains your battery, so you rather should go to low range. And then, of course, for tablets and so on, you have larger batteries, so everything shifts to the right. But the interesting conclusion is, as a wireless guy, I would say use 4x4 to get the highest data rate. As somebody who has to live with a limited battery, I would say don't do it because the battery, you need a power plug very soon. Now, these results were based on 65 nanometer technology, and you could say, okay, 65 nanometer, today we are at, let's say 22 or even below 40 nanometers. It always depends a bit on how you scale it. So will life be easier in the future? So what I did is, I picked up this slide again. We just saw this in the beginning of the talk, that the scaling is going down to 5 nanometers. That's what's predicted. 2025, well, that's almost 10 years from now. So should we really have to worry that there is maybe some end in 2025? Let me get back to wireless communication. You can, it's not 100% correct from the timing, but you can roughly say that one generation is 1 decade. 1990, it started with GSM, first digital system, 2G. Around 2000, it was UMTS, 3G. Around 2010, we had LTE as 4G. And people are working on 5G, and it's expected to be launched soon in 2018, 90, 2020, around that. So it's roughly 1 decade. So 2025 falls in the middle of the 5G decade. It's relevant. It's not that far away anymore. So what's going to happen actually? And it's not as nice as I showed before, because expanding to 5 nanometers and for the next 10 years sounds like, yeah, okay, the end is visible, but until then we have no problem. This was the figure that I showed before, and I would like to remind you of the purple line on above, which is the Moore's law, which is indicating how the number of transistors increases. And this refers to this famous 2x every 2 years or 6x every 10 years equation for Moore's law. Now let's take this into the future. So if we go from 2030 to 2025, this would be the gates per area, so the density, so how much we can do over the next 10 years. But actually, the scaling as it's defined by ITRS is this green line. So it's lower. And actually this is just a geometrical scaling. The actual scaling that we have is not as good. It's actually again a bit lower. It's this blue line. That's what we can expect really. And now it looks not very dramatic. It looks like it's just half of the red line. Unfortunately, the left-hand side is a logarithmic scale, so it's almost 1 order of magnitude below. So we will fall 1 order of magnitude behind Moore's law. So the future, the next 10 years, will not be as good as the past 40 years from that perspective. We will get more problems in the implementation. So we will not have more than 10x over the next 10 years. And before it was half the time for 10x. And that's 10x or 100x is significant difference. But that's not all of our, these are not all of our problems. There is one more, and this is power. When the transistors get smaller, they consume less energy per switching or less power for a given frequency. But they get smaller, so they get denser. So we have less energy per transistor, but we have more transistors per area. So we have to consider the product for the power. Why? Because power is converted into heat, and we have to get rid of the heat. So if we take the energy density, we see it will grow a bit. So the factor of energy reduction per transistor and density is only slightly increasing. That's okay. But of course, the clock speed, the chips will get faster to get the same processing gain. And that means we also have to consider this. The switching will occur more often, which means the power increases more. So we actually have something like a duplication. And that means we come to power densities which are very high. So partly, if you drive it to the limits, you would get to something like inside a nuclear reactor. So you somehow have to get rid of the heat. And that is the problem. So I've shown it here with the chips that we have done more or less. You have the same heat, and the area is only half the size, and that makes it more difficult to get rid of the heat. So power is not just a question for the battery, it's also a question for heating the chips. dark silicon and so on here, so I want to keep it more on the communication level, and because that already is enough to show the problems that we have here. Actually, it's a bit worse than I'm showing it here, so it's almost an optimistic view. So, does this mean a new design paradigm? Actually, we have currently a research project which is in a special program of our National Science Foundation, the DFG, and it's targeting and transmitting 100 gigabits per second and beyond. We already learned that power is an issue for the heating. So how do we avoid that the cell phone at 100 gigabits per second starts to just burst out in fire and smoke and die? To understand this, why this is a problem, I have here a short, simple calculation. And this calculation says, if you take a device like your cell phone, you don't want to have a fan inside. In your PC, you typically have a fan on top of your processor to have the forced cooling, but you definitely don't want this in your smartphone. So, we only have unforced cooling in there. And then the heat that can be dissipated is limited. It's a few watts, so I have taken just 1 watt as the order of magnitude. It's a bit more, but to show the problem, it's enough to discuss the order of magnitude, so let's take the number 1 watt. And assume we want to transmit 100 gigabits per second. If I divide 1 watt by 100 gigabits per second, I find out it's 10 picojoule that I have per bit. So for processing a single bit from the antenna to maybe the application that's using this bit, is 10 picojoule. Okay, what does it mean? Well, NVIDIA, very well known for advanced processing, graphic processing and so on, they made an extensive study and they found that 28 nanometer CMOS technology, which is the previous generation, you can do 1 to 2 operations per nanojoule. So this is already 2 orders of magnitude, about 10 picojoule. Okay, we have the technology scaling. We are looking into the future. So what about 7 nanometer? We have this power scaling. Unfortunately, the power scaling will not work as strong. They already saw that before what the problems are. The factor they found out is around 8. So we can do 8 times as much, which means 8 to 16 operations per nanojoule. Or if I go for the 100 gigabit example, I have 0.08 to 0.16 operations per bit. So I cannot do even 1 operation per bit. There is one thing in our favor, that is when NVIDIA talks about an operation, they take an instruction from the memory, take data from the memory and do the computation because it's a processor. If we do it in hardware, we can do it more efficient, so we probably can do some operations per bit, but we see where we are, it's tight. And this was the positive side. The negative side is there is also AD conversion and DA conversion, and this is something which is very power hungry. And these numbers are for 7 nanometers, which is only available in 10 years from now, not today. So, shouldn't we have a new design paradigm? To study this, we have analyzed what this means for the communication system if we run into such a problem here, if we really take into account that we may run into a power problem. To do this, we did not go for low frequencies, because when you only have a few hundred megahertz of bandwidth available, if you are below 10 gigahertz, you typically have at most 500 megahertz to 1 gigahertz. That would mean you already need for 100 gigabits per second 100 bits per hertz, which is a 2 to the power of 100 QAM scheme, and you can imagine this is totally out of scope. So we went to higher frequencies around 60 gigahertz or beyond 100 gigahertz, because there we have at least a bit more bandwidth to do this. But the question is, how many bits per second is really possible when we take into account that we run into this power problem on the chip? And is there a reason to change the wireless system architecture to get to this maximum range? And yes, the interesting result so far is there is a reason to do that. And I cannot go into all the details of what we studied there, but just give some indication of where this is going. The first thing is you would not want to use really OFDM. There are various reasons why it's bad if you have power constraints. And one of the reasons is OFDM has a very high peak to average ratio, so your signal has a strong fluctuation. And you have to maintain this, to get this out of the antenna. So your power amplifier has to be linear over a wide range. And that means the power amplifier is inefficient. So that's one of the reasons. Also in the AD conversion and DA conversion, you need a lot of headroom to do this. And that makes the power consumption in the converter side. So OFDM was not a choice. But then we have the problem we don't get flat fading, which means MIMO detection is difficult. But we found there is a different way, because in particular when you go to higher frequencies, then you have some distinct paths and you can separate the paths, you can compensate the different delays. So it gets a different architecture in doing this, and that architecture is much more power efficient than using OFDM. And even you have some things to play with, because when you want to use these different paths, you use beamforming, electronic beamforming. You can do the beamforming digital, you can do the beamforming analog. Analog is typically more power efficient, so you can do some trade-offs in how much you do analog, how much you do digital, and optimize the structure. So these were some of the things that came out of it and showed that if you are really targeting for very high rates, and you consider that you will run into this power and heating problems, you get a different architecture than you would get if you just would take the view of a wireless communication engineer. We definitely tell you take OFDM and life is easy. So how did we get to this? And why is this changing the design paradigm? Well, we said we cannot just look for wireless performance, we also have to look for the energy budget. And the energy budget is of course not yet known, you have not built it. On the other hand, you are thinking in orders of magnitude, so you don't need to know the numbers, the digits behind the comma or the point, the decimal point, so you can just deal with rough numbers. So for the RF part, we have some analytical models that were based on measurements and state-of-the-art models. The beamforming, when it's done analog, you can also get power numbers for the different components that you need there, so you can give some analytical equations on what it means. And for the digital part, we have models for some of the functionalities. So for processors, for instance, we have very good power models. For other specialized components, we just made a netlist, and then you make a netlist simulation, and then you get quite good power data. So there are different ways how you can put it together. So overall, what happened was you take your wireless communication parameters. From that, the analytical model tells you what power is consumed in the RF part. The modulation and coding, the digital part, is by simulation and power modeling. And for the beamforming, which is semi-analog digital, we also use analytical model. That gives us a number. This number, of course, depends now on what technology you want to use. There are quite good predictions about the performance of these technologies in the future, and how they depend on different tricks that you can do. So we do a scaling based on these scaling factors, which are available from the semiconductor people, and then you get the power for your design, and you can decide, okay, yes, that's good, or that's bad, I have to change things. Or not. Of course, everything has to be added up to give the final total number, which is then the relevant comparator. So, with the motivation, and here's some idea how to deal with it, I would like to finish this by going into a very short outlook to the future. So again, I come back to the slide that I already have shown twice with this prediction down to 5 nanometers. you could of course say if 2025 CMOS ends at around this year, is it really the end? Because this end has been predicted several times in the past, and you could say, well, it could continue. I wouldn't bet on this one, because this lower sentence on the left is from Wikipedia, so it must be true. No, seriously, it's a well-known fact. Silicon, on the right-hand side, you see the silicon atoms with its electrons. It's said to have a diameter of 0.1 nanometer, but actually in the cubic crystal that we need in the, for silicon, it's about 0.5 nanometers. So 5 nanometer means 10 atoms in a row. So even if you take a block, it's very few atoms, so it's countable numbers. So if you cannot go much lower, because then it starts to become quantum physics. So that doesn't work. There is an end around this. Now you could say, this is a very desperate situation. We should all start to look for a different job. Wireless communication has no future. Technology will not support it anymore, so life comes to an end. No, I would say we should look for a new system design paradigm. As I've shown it, take the limitations into account, and also don't try to build a system that's capable of doing everything. I guess 5G will be the last system that claims to serve every purpose, from IoT to video downloads with HDTV quality. Rather, look at combining wireless communication with the application, make this efficient, and make the combination efficient. So not just look at wireless communication on one side and make it a system that serves everything and then attach something to it, but look at the complete application. The other hope could come from technologies beyond CMOS, which in this community is sometimes called more than more. And I've just identified 3 major directions here. You could argue if there are others, but I think this is roughly giving the main points. You could go into the 3rd dimension. So far we have talked about squeezing the area, but we could start to build layers on top. Unfortunately, there is no real technology to do this. The main thing to do it is to stack things onto each other, and that's not really scaling largely, because you cannot stack thousands of devices, then you have problems to get rid of the heat, you have problems in maintaining manufacturing quality, and so on. So this is very limited. New components. There are a lot of new components in there, like resistive switching, like ferromagnetic spintronics, and so on. They don't provide really much more density, but they are interesting because they have different features. They have partly inherently included memory, so you might actually use different system architectures and make more out of the system by taking advantage of this feature of this component. So that could be an interesting thing to look at. And last but not least, the biggest look into the future would be quantum computing or DNA-based or biocomputing or whatever. Well, the question is, when will it be available? I may be pessimistic, but I know that fusion reactors have been promised as the solution to energy 50 years ago, and they are still promised as the solution for it, I guess, for the next 50 years. So the question is, do we get quantum computing? Is quantum computing really able to do wireless communication computing? I don't know. So this is the most uncertain part. So I'm currently more set up at the first point here, and I think we can learn from the colleagues, because I found in the presentation from last summer the rebooting computing initiative, because the compute guys have the same problems. They have the same problems with the power consumption. So they know that to get to exascale computing, it's not just enough to continue as today. You have to really redefine how we do computing. And they started an initiative, rebooting computing. And so my recommendation would be, think about rebooting wireless communication and taking this into account. So instead of a question mark, I will put an exclamation mark here at the center. And with this, I'm at the end of my presentation, and thank you for your attention.
more advanced type of communication system, or never think about how to implement or internal to energy. Now it is apparent that, you know, even though you just come up with some kind of novel ideas, it may not be end up with a feasible solution because of this energy constraint about that. So that's from, you know, from that respect, I'm going to just tell one thing about special migration. You know, recently the people are working with massive MIMO. Then I realized that, you know, for the implementation point of view, I mean the massive MIMO, it will draw enormous amount of energy. Then it would not be, I'm not sure exactly, feasible for the 5G or beyond the 5G type of system based on this massive MIMO system. What do you think about that first? The second, you know, the special modulation could be a remedy for this thing, because you know that, I'm sure you know the basic special modulation. Rather than using all the antennas, for example, we choose only the subset of antenna, and then we transmit the information from those antennas. But at the same time, we transmit the label, information internal to label of the antenna we choose this one. So I'm expecting that the amount of energy that we use per bit would be reduced substantially by using this kind of technique. But still, I mean, those are the very limited type of approaches. That one. That's one of my first observation.
Yes, I think it's actually the point is here saying it's not hopeless. The question is, the point is consider this here. But massive MIMO, for instance, it's a yes and no. I mean, by using a large number of antennas, a lot of things get easier. So it's not just a penalty, but it's, and also when you look at the transmit power, it's not like you transmit the same power as with a few number of antennas per antenna, but when the power that you transmit actually stays almost the same, or it even decreases. Because if I use one antenna, I radiate omnidirectionally. So the energy is going everywhere. If I use massive MIMO with many antennas, I radiate in the direction where I want my information. So actually the total amount of information becomes smaller. I have more paths, but each of these paths has a lower power consumption. So it's not like that this is actually positive in the sense rather than negative.
In the manipulation point of view, as you said, I mean, reciprocal complexity become enormous. I mean, you know, just think, massive MIMO, you know, channel estimation, detection, those kind of processing, all those things. I'm sure that, you know, enormous.
This is a trade-off to be analyzed, and I don't have a clear answer right now what the cost will be, because it depends a lot on the channel environment and so on, how much effort it is. On the other hand, we are talking a little bit of the panel discussion for tomorrow. I would say this the big future on this is probably when you go to the higher frequencies, because at the higher frequencies you can integrate this stuff much better. It's all smaller, so many antennas at 2 gigahertz is a big array. If I use the same at 60 gigahertz, I have a 30 times smaller array because the wavelength is smaller. So going to higher frequencies could, for instance, be a very good path out of this problem. And actually, on the last Mobile World Congress, Ericsson, they demonstrated this. They had at, I think it was around 10 gigahertz, they had a system, an array, and so they radiated, it was not massive MIMO, it was many antenna kind of system, but they were able to direct these beams to a mobile device in an environment, so they could support gigabits per second over for this moving device easily. Yeah, well, there are some things like graphene, for instance, or nanotube, but this will even be a completely different architecture probably, because you would not build from nanotubes, you would not build a system like today with this kind of transistor, because the electronic behavior is completely different. So this would be more, would actually mean you have to, this would fall under this part here, new components requiring also new architecture, because then you have to think that you do things differently to make it efficient.
So finally, just my observation, since you said that we are far from becoming all digital, I guess that we're still far away from the ideal software-defined radio, which has to have other digital components to be efficient. But anyway, thank you very much. This was very interesting.